All right, we'll go ahead and get started. Sorry for running a little bit late there. Just I was right in the middle of trying to polish up this presentation. So we'll get started. Thanks for joining us for the proper installation, and why it matters to the energy code. I know we've talked about installation before. We've looked at grade 1, grade 2, grade 3. I just wanted to put the relationship together on what energy inspectors do when it comes to looking at the energy model and how it's verified and confirmed for compliance in the field. So we're going to talk about that today. So let's go ahead and get started. We've got a lot of information to cover. As always, today's webinar is being recorded. It will be uploaded to our YouTube channel, which you can find by either searching SPEAR on YouTube, or you can go directly to our website and go to eepartnership.org. And under our news section, you'll find our resources page. Once you're on that page, you can look for our link. It should show up right there at the top right. It's the link to our YouTube channel. Within 72 hours of today's presentation, you receive a course evaluation email from Kathy Lawrence. Please complete the survey and send it back to her to receive your course completion certificate. That will contain your course ID number that you'll need when you're reporting your CEUs to ICC. And as always, any feedback you can give me helps tremendously. So what we've covered, what we haven't covered, what you'd like to see us cover, if you didn't think it was enough information, please let me know. We'll do an update on it and we'll go through more detail. I only have hour to hour and a half to do this, so I just kind of put a lot of information in one package. Sometimes it's not as in-depth as it should be. Lastly, the chat feature is open. Use that to report any technical difficulties you might be experiencing during the presentations. Also, I have the Q&A feature open. We'll answer questions as they come through. And as always, at the end, I'll just stay online after we stop the recording, and we'll just have an open discussion if you have more additional questions to ask. So let's get started with this. So those that are first time being on here, who is SPEAR? We talk about this all the time, but we are kind of what we think of ourselves as the training arm of State Energy Conservation Office. We provide trainings, webinars, in-person field trainings, as well as ICC test prep on a one-on-one basis. I can help with questions regarding energy code, ASHRAE 90.1. We can help with questions that relate from plan reviewers to building officials to third-party inspectors. I'm happy to help in any way that I can. We've also assisted several cities, and we're still doing that, in their adoption of a new energy code, be it whether the 2021 or now the 2024 that will be out in the beginning of next year, and how to navigate through all the additional amendments to try to help lessen the impact of the adoption for your building and your constituents in your city. My contact information will be at the end of the presentation. Please feel free to reach out to me with any questions, snap a picture of it, screenshot it, share it with whoever you think needs to have that. I'm trying to get my name updated up on the SECO's website, but there's still a lot of people that reach out to SECO first, and then they go by avenues of talking to Jason, which is now with NEMA, and then he passes them on to me. So feel free to share my contact information with anybody that needs my help. So today's agenda, we're going to go through the understanding of the energy code. Some of it will be kind of elementary, but it still bears for us to be able to explain it. The importance of proper installation, why it really matters, what does the code say about the installation, understanding kind of a basic of heat transfer and why, again, doing installation correctly matters. And then identifying the building thermal envelope. The R value is going to be explained slightly, just one or two slides. Types of insulation we'll see out there in the field. Insulation by component, and then how much difference does it really make? So a lot of people ask that question of, well, it's insulated, may not be the best, but how much difference does it really make? And we'll look at how that actually translates into the energy code in our inspection. So where to start? So it's almost Halloween. All of you third parties that are out there, if you're looking at this picture, it's one of those things. I just thought I'd put a scary picture up. When I walked into a house that looked like this, I mean, your heart just sinks. You now realize that your day will be long, and you depend on what you're going to have to do. So is it a correct and proceed? I mean, if not, I don't know. Maybe it's a dry run. You move on. The builder's not going to enjoy the phone call. You have to talk to them about what you're seeing, what you're looking at. Worse yet, he may ask you, well, can you mark up all that needs to be corrected? That, again, is a heart-stopping moment of, how many cans of spray paint do I have? Do I really want to get up on a ladder and do all of this? Do I really need to spray all this up? This is never fun. Thankfully, this was called in before insulation. Otherwise, you may not see over the patio. You have to walk outside and look at behind every single one of those walls to make sure it's done correctly. But open exterior walls, open knee walls, open chases, hard to insulate vaults. This is just a nightmare, in my opinion. This is a Halloween-worthy picture when you walk into an inspection. So understanding the energy model. So before we get started about talking about grading of insulation, we need to first talk about the energy model and why and how it works. So to do that, we need to talk about the software being used. We've talked about these before. We've got ResCheck, ComCheck, Ecotrope, Rim Rate, Energy Gauge. There's always new ones that are on the horizon that may be coming out that helps third parties verify these things easier in the field in real time. Just like with inspectors, though, the more you have, the more room there is for inconsistency. So each one of these use their own engine. That's the algorithm in the background. It calculates things differently. That said, they're all acceptable softwares, but each of the report can report a different outcome. So this doesn't make them incorrect. It just means that something was calculated differently. One of the softwares you may be using over the other because the same house passes in one of the softwares but won't pass in another software. It's just how they're done differently in the computations behind the scenes, the engine that drives it. Third parties across the country diligently report their findings to software companies and who can then adjust these algorithms, adjust the engine as well. So case in point, when the climate change or climate zones changed across the country, especially in Dallas-Fort Worth, with the 2021 IECC, some were still using older weather data in their previous maps. So they didn't link that to the new weather data that was supposed to be associated with the newer or different climate zone that happened in those areas. So with that, some of the companies are slower than others in fixing these types of issues. So there are these issues that are out there, but we rely heavily on third parties to find those differences and find those areas of concern and report that back to the software companies that can then adjust it. Some are slower than others. Some may take a while. Others may think that it's not that big of an issue and they're not really changing it. So it comes down to the fact that there used to be third parties that would only use Rim Rate or only use Ecotrope. Now I see more and more of them using both because some have an advantage and others don't have an advantage, and you change it from what actually fits the needs in what climate zone, or if that city that you're building in has changed climate zones, it may be easier to go one or the other because something hasn't changed in the energy model. So what is the energy model? I mean, really, with that, an energy model is a computer-generated set of calculations that predicts the anticipated energy consumption of the building and its systems. It's a whole building energy simulation. There's also, you're right, Izzy, thank you. There is an IC3 that's out there. It is available. I didn't put it on that slide. That was my bad. That was developed by Texas A&M. So IC3 is still available. It's used to simulate the energy usage of a building with software that analyzes multiple aspects of the building and its systems and generates crucial information to optimize new and existing buildings. So energy models can help engineers and contractors compare energy consumption in different scenarios using different materials and equipment. But with that being said, it's up to the inspector, a building official, third-party verifier, energy verifier to now know what that model says and then inspect to what that model said it needed. So it could differ from every single home. So energy model calculations are calculated in an hourly energy usage and it's reported as annual figures, meaning it takes local historical weather data, uses it to predict, to simulate the energy use used by the building for each hour of the year, and then totals and reports them in an annual usage. When reading an energy report, you should be looking at the totals that are being compared to the referenced home, and we'll see more of that later in the presentation and what that looks like on a report. The referenced home is that's really important to know, and it's kind of lengthy with this part of it, but the referenced home is when you're constructing the energy model, particularly for the purposes of code standards and energy efficiency, a referenced home, also listed sometime as a baseline home, is used as a comparative tool. It's essentially a hypothetical model built following a predefined set of criteria against which the proposed design is being compared to determine the relative performance and efficiency of the building. So with this, you have the purpose. So you have to compare it So by having standard baseline, it's easier to quantify how much better or worse the proposed design is. Standardization basically provides a consistency point for reference across different designs in the locations and different building types. You got regulations and certifications. Some energy efficiency standards and codes require buildings to perform better than the defined referenced home to qualify for certification of approval. If you were part of our 2024 rollout when we did it last week, it used to be if you did performance or ERI, you had to be equal to or better than, but it would just say equal to, in other words, 100% or better than the referenced home. Now they're tightening things up and saying you have to be 85% or better of the referenced home. So you know that you have to know what code you're following and what difference it makes. With the characteristics, it's defined by standards. So the specifics of the referenced home are usually established by building code standards or energy efficiency programs. For instance, the U.S. Department of Energy's Building Energy Codes program provides guidelines on how the referenced home is to be constructed in the energy model for comparison of the design being built. Static criteria, while the proposed design can incorporate a variety of innovative techniques and technologies and materials, the referenced home technically or typically has a set unchanged list of criteria. These might include specific insulation values, window types, and HVAC equipment, or efficiencies, size, and shape. The referenced home it will be the same size, it will be the same shape, the orientation of the proposed building as the proposed building to ensure the direct comparison. However, its construction details like systems and equipment efficiencies are set on the predetermined standard on what you're following. So if it's Energy Star, it will be different. You're actually comparing an Energy Star home to a base model code being built. That's the referenced house. And then when using the referenced home in the energy model, you have simulation, which is both the referenced home and the proposed design are simulated under identical conditions. This provides an estimate of annual energy consumption for each. Then you've got performance comparison. The energy use of the proposed design is compared to that of the referenced home. If the proposed design consumes less energy, it's said to perform better than standard. Percentage of improvement, basically you can look at it and go, how much better is it? Then you've got applications, you've got code compliance, so just showing code compliance. Some incentive programs are out there that says you must have an ERI, you must have a HERS score, you must be Energy Star. Those things are determined also by the energy modeling. And then design feedback. By comparing a proposed design to the referenced home, designers can identify areas of improvement, make data-driven decisions for enhancing energy efficiency. And the importance of proper installation. So proper installation of building is crucial for several reasons, all of which contribute to the overall efficiencies, comfort, safety, sustainability of the home, and is a key aspect for residential buildings due to the wide-ranging impacts of cost, comfort, health, environmental sustainability, and overall building quality. So energy efficiency, we all know that. I mean, if it's not insulated, it's very poorly energy efficient. Reduces the need for heating and cooling by minimizing heat loss in the winter and heat gain in the summer. It leads to lower energy consumption, which means fewer greenhouse gas emissions from heating systems and air conditionings. And as we talked about in the 21 and 24, greenhouse gas emissions and carbon footprint is playing more of a role of the energy code. Cost savings is decreasing utility bills due to reduced energy usage. Can also lead to potential tax credits and rebates in certain jurisdictions. Comfort helps maintain a consistent temperature throughout the home. There's avoiding the hot and cold spots, and you have convective movement due to hot and cold spots in a home. Some people list them as it's a draft. It's not really a draft. It's air moving due to a temperature change or a pressure change. Reduces noise pollution by acting as a sound absorber and creating a quieter home. Then you've got moisture control. So proper installation helps prevent the buildup of moisture in a wall and ceilings, which can lead to mold and mildew buildup. Controls humidity levels, contributing to a healthier home. As we talked about in previous insulation webinars, the more poorly the wall or cavity is insulated, or the floor is not properly insulated, you're moving the dew point inside the wall. So if you move it too close to a cold surface, either the interior conditioning side or the outside in the winter, you're moving that dew point to possibly add to moisture issues. So improved indoor air quality. So by managing moisture, reducing potential for mold, mildew growth, proper insulation contributes to better air quality inside the home, enhanced building and durability. It all goes back to moisture mitigation. Air movement can lead to structural damage. Then you got safety. It reduces the risk of fire spread, as many insulation types are flame retardant. Prevents the formation of ice dams as well in cold climates to keep that from actually deteriorating the building itself. Increased property value. A well-insulated home has a higher selling point, potentially risking market value or increasing the market value. It shows the home as being well taken care of and updated. And then regulatory compliance. So meets building regulations and standards for energy efficiency, potentially avoiding red tags and reworks. So stays current with updated building codes and the environmental legislation. What does the energy code say about this? So looking at this directly out of the code, it says the components of the building thermal envelope shall be installed in accordance with the manufacturer's instructions as applicable to the method of construction. And to the right, I pulled off of Google, just straight off of, I think it was Owens Corning. This was their general installation instructions for fiberglass insulation in wood and steel framing. So the product is designed to friction fit. No stapling is necessary. The insulation should completely fit snugly within all framing cavities with no voids, areas of compressions, or gaps between insulation and framing members. That is grade 1 defined right there. For cavities with obstructions, insulation should be split or cut to ensure insulation fills the cavity both behind and in front of the obstruction, avoiding gaps of areas of compression. Again, redefining grade 1. Insulation should be cut to fit snugly around electrical boxes, not bowed out. Place the cut out portion behind the box to fill the void. That usually doesn't happen. Someone just sprays a lot of polysil behind it, doesn't fully insulate. It has some insulation to it because it's trapped air, but it's not insulated to the same value that it can if you use bats. For cavities of non-standard height or width, cut insulation approximately a ½ inch greater than width. This is basically saying it needs to be cut to fit. So cut to fit, and cut to fit means by manufacturer's instructions, you cut it a ½ inch bigger so that it can be friction fit and fully in contact with all sides. If you don't, it'll leave a gap. And then understanding how heat transfers in and out of the building. This will just be really quick. We're just looking at conduction, convection, and radiation. With all of these, the insulation has one job. It's to slow down all three. And when you slow down all three, yes, radiation is in the air. It moves without insulation. But as we talk about, when radiation comes through the sky, comes through the air, the earth, it comes through the envelope of the earth, and then it actually hits any kind of surface, that radiant heat turns into it starts heating that material up. And that heat in that material, if in contact with anything else through conduction, it transfers its heat. It can also re-radiate that heat through convection. So insulation is there to slow down all three of those. That's how it makes its way into the building. When an inspector goes into and starts to identify and starts to inspect how well the insulation was done, the first thing out of the gate they need to do is identify the building thermal envelope. So it's defined as all building element assemblies that enclose conditioned space or provide a boundary between conditioned space and exempt or unconditioned space. It used to just say unconditioned space. They've added the word exempt because there may be areas of the building that's listed as exempt and not having to be insulated depending on the climate zone. So this was a chart I pulled offline, kind of found it interesting. R value, it's just showing how the R value is determined. It says in the US, the R value of insulation is determined by using a standard testing method called guarded hot plate test. The test is conducted in a controlled environment where there is no air movement at a temperature of 75 degrees. So if you list the R value of something as R13, that's without air moving through it or around it or in contact with it. When you do that, it lowers the value of the R value. So R value is just a measure of thermal resistance. More specifically, it quantifies the ability of the insulated material to resist heat flow across it or through it. The higher the R value, the greater resistance to insulation and insulating effectiveness, meaning that less heat is lost in the winter and less heat is entered in the building through the summer. Looking at this graph, though, we actually can see It's if you change the temperature by making it get hotter and the temperature goes up, the R value starts to diminish. So the key factor to why insulation is required to be encapsulated on all 6 sides comes down to this. If you can better enclose the insulation, not have air in moving through it, or different temperatures against it, it upholds its R value longer. It doesn't diminish the R value. You have it exposed on any side at all with different temperatures, it can lower its effective R value. So if hot air is allowed to be in part of that, and you actually get to that cavity, so it just drops. As you can see, though, all material loses its R value. All listed material on this chart. There may be others out there that are different, but on this chart, it's listing polyiso, it's listing the XP, the EPS, it's listing fiberglass or mineral bats, the low density, the high density, the rigid board, cellulose. All this stuff is listed here, and if you see the temperature going up, it just starts to drop. I'm not sure what really happened with that blue line that's there. That's listed as the half thickness of SPF. I'm not really sure why it started low and shot up high, but that's probably a deviation in their testing. So how a rater determines proper installation, how do they grade it? So that's what we're going to get into now, is grading how well the installation of insulation is done. With this, it takes, in my opinion, it takes months of practice and experience looking at things over and over again to where your mind finally can see the differences. And so it's easier for me to do this like this, but it's 2-dimensional. It's not 3-dimensional. It's harder to see in photos than it is in real life. But this is kind of how you start, looking at pictures of differences and saying, I know why one's a grade 1, one's a grade 2, and one's a grade 3. A great way to ensure consistency, though, is to create checklists like this. This came directly from Owens Corning. It basically just shows a pre-check and then a self-check. And it's looking at insulation criteria details, top and bottom plates of all exterior wall and party common walls and all floors, and vertical members at foundation steps down and sealed or gasketed. There is both a top and bottom plate installed in each knee wall. All knee walls are backed with rigid material. And it's also looking at skylight shafts, walls adjacent to porch roofs, staircases to attics, staircases to unconditioned garages. All shafts and chases are capped. All floor system cavities between conditioned and unconditioned floors are separated and blocked and air sealed. Then it goes through saying at the bottom, then it says self-check. Insulation is installed without gaps, voids, misalignments, compressions. Insulation materials in full contact with all sides of the cavity. Insulation is cut and split around blocking, plumbing, HVAC, and electrical components. Frame floor cavities shall be completely filled with insulation, or the insulation is installed to permanently maintain permanent contact with the subfloor decking or the conditioned side. Insulate any overhanging floor cavities before closing them with rigid sheathing. We keep seeing photos of that not being done. Insulation is installed behind showers, tubs, staircases, fireplaces, on exterior, attic, and party walls, and rigid sheathing and or other supporting material is installed to hold insulation in place. That gives us the whole, there needs to be an air barrier on the inside and hold it in place. Access panels, attic, knee wall, drop down stairs, whole house fans are weather stripped and insulated the same R value of the surrounding area when possible, minimum R10. So that kind of goes without saying, with if it's possible, insulate to the same. If not, and it's too difficult, R10 is acceptable. With this, additional items affect the R value. Air infiltration, we just talked about that. You let air into the cavity and it diminishes the R value. Simple as that. And then extreme temperatures, both sides, inside and out, we talked about that too. If it's missing a block on any 6 side of the cavity, you're now exposing it to extreme temperature differences, either cold or hot. And then you've got thermal bridging. So framing material that surrounds the insulation, the more framing material used, the lower the R value, or the overall R value of the thermal envelope. So if you're looking at a wall, you're saying that's R13, but there's a ton of framing that happened. And I understand a lot of it has to do with loads, and that's fine. If it has to be for load-bearing reasons, then you can't say anything about it. But if they don't use things like advanced framing, and they don't use ladder blocking on T-walls, they don't use 2-stud corners in the corner, then it just basically the overall R value of the thermal envelope drops. So that's the main reason why above code programs like Energy Star Lead require advanced framing techniques to be used. If they're not, it's an automatic fail and you cannot certify for that program. I found this interesting as well. This actually is a comparison of the advantages of SIP panels. So over traditional framing, SIP panels are structural insulated panels. It's basically expanded foam trapped in between two OSB boards. It's a great representation of how thermal bridging like stud lowers its effective R value. On this, we see the SIPs without all the studs. It maintains and can help perform as an R14 in an R15 cavity wall. Like if you're doing R15 high-end density bats, then you're comparing it to SIPs. Its overall effectiveness in that same wall is R14 compared to a 2x4 wall that's 16-inch on center. Its effective R value is 9.6. And then only a 2x6 wall with 24-inch on center with the quality installation, aka grade 1, comes in a close second of R as 13.7. Anything else like a typical grade 2 wall in a 2x6 24-inch on center immediately drops to an R11. And then you've got a 2x4 on 24-inch on centers, it's 9.8. So as we see, it lowers the R value the more studs that you have. It's the overall R value that's in that wall, not each cavity, but an overall of what's in that. The models actually take all of this into consideration. They look at the framing, 16-inch on center. They take all this thermal bridging in consideration when it actually shows the usage, the consumption of energy, and how to condition the building. It actually does all this on its own. That's why grading it as well is also key, because not only do you have a 2x4 wall with R15 bat performing at a 9.6, now you grade it as a grade 2, it's going to drop that 9.6 even further. And then, of course, you punch holes in the wall and call it windows and doors, and now you have a problem with that as well. Yes, Cody, you're right. Compression also affects the R value. Absolutely. Thanks for joining, Cody. I appreciate it. But this just shows, again, it's difficult for third-party verifiers to look at, call something out, and then red tag it, and then have a, not trying to pick on anybody, but you have a building official say, well, it's insulated. I don't see anything wrong with that. Well, there's a big to-do wrong with that. It's how well it was insulated. And that's the job of a third party that they have to do to pick this out and be able to do it on their own. So looking at some of this on the critical details, I just pulled this off of Owens Corning. Looking at that, and you got gaps and voids, just showing an incorrect and correct. Yes, it's a paperback material, but you can still see the same thing would happen with a void at the top. No compressions, misalignments. You got incorrect on the left, and you got correct on the right. It looks really nice, looks really pristine. It's still friction fit. On the left, they've pushed it a little too far into the cavity. And then cutting around wires, left, incorrect, right, correct. You got to split it around there. Either you tear the bat in half and lay part of it in the front and back. You could also cut it horizontally and then actually let that meet together on that wire. It doesn't necessarily have to be split. And then on the right side, we've got an incorrect on the left showing gaps, misalignments. On the right, that's what I talked about earlier, is you see it correctly cut around the electrical box. But on the left, you kind of see they just let it bow around it. They did not cut it, so it leaves a gap at the top and the bottom. It should be accurately cut around it and then fitted to that. And that piece should really go behind those boxes to actually meet that inner insulation levels behind it. And then also we're still looking at compressions. We're still looking at misalignments. You see compressions on the left. You see it correctly done on the right. That on the right would be a grade 1 all day long. But then you start looking at floors over anything, floors over garage, floor over crawl space, floor over unconditioned basements, floor over the outside. And you look at, is it properly placed in the right location? Is it in contact with the conditioned side? This is a quick, easy side snapshot of it's not. On the left, it's not in contact with the floor above. I'm assuming that this is a garage we're standing in. It may not be. But it's not in contact with the floor above. And then right, they are fully filling the cavity. They are cutting around obstructions that are inside that cavity and then fully filling it. I'm hoping that she's just not finished with the job and that gap that's behind the pipe is still going to be filled. Probably will. And then floor over ambient, we're looking at that, shows cantilevers, overhangs, actually seeing that before it's covered with anything, with OSB or cornice boards or anything, to make sure, is it insulated properly? This is showing a rigid board that's there. It should also be, seeing that its depth is that, it should also have full insulation depth in there to actually be in contact with the floor above that's being conditioned. And then you got behind tubs, showers, and fireplaces. I had a call just this week about this specific thing. As you see on the left-hand side, it's a fiberglass enclosure. And a lot of them are doing, this shows no insulation, but these were insulated with bats, but it wasn't in contact with the enclosure. And they're not putting any barriers in front of that insulation to fully encapsulate all 6 sides. They're allowing the enclosure and fiberglass tub enclosure to be its air barrier. And as I said before, that, as I told them, that's correct. It can be if they fully fill the cavity with insulation. So if they're using bats and they want to use it as their trash bin, they can just stuff it full of insulation. As long as it's in contact with its all 6-sided air barrier, it is acceptable. But leaving it without an air barrier in front of the insulation and in contact with the insulation, code really specifies that this needs to be encased and encapsulated on all 6 sides and air sealed all the way around it, which means they call out specifically tubs and showers and fireplaces need to have an air barrier installed on the interior side, below tubs, below and behind showers, and in the back of fireplaces. And then with that same kind of thing we just talked about, it lists the same thing: tubs, showers, and fireplaces. It listed that as well, and it's actually showing bats against the back wall of that fireplace, but no air barrier on the inside. That's a misalignment of the air barrier. If you're going to have sheetrock in front of the fireplace, yes, that's an air barrier, but now you've got a separation of thermal and air barrier. So Matt actually says behind showers and tubs is one of the biggest struggles I have when doing insulation inspections. I agree, and I appreciate it. And Matt was the one that actually emailed me about this and said, how do I enforce this? You really have only 2 options. I mean, you either have them, they have to remove the tub enclosure and add another air barrier in front of it, or they can fully fill behind it with insulation. Now the tub is its air barrier, but they have to be in contact with the insulation. Otherwise, it's a misalignment, kind of like we're seeing in these pictures here. And then, of course, if the attic access can be insulated to the same insulation around in the attic, that's great. If it can't, at least the minimum of an R10 is affixed to the back of those scuttle holes. But a lot of times I see that scuttle hole cover, there's a bat there, but it's not affixed to it. So the first time someone does an inspection, it just gets thrown out of the way and it's never re-insulated. That really should be somehow affixed to that. This is a paperback, so if you just have some spray glue or anything like that, that'll actually stick to it. If you have a regular bat without paper, it's a little harder to get glue to hold. It still can be done. Proper installation. So proper installation for this. So we actually have a question on here. How can a balcony be properly insulated? Balcony. So that can be determined differently. Is there a conditioned space above or below the balcony? If so, it needs to be like what we just saw with the cantilever. It needs to be insulating whichever side is the conditioned side. It needs to be in permanent contact with that conditioned side. If you're talking about a balcony that sticks out of, let's say, of an apartment, and you have the actual exterior wall being insulated, you got to have an air barrier on that too. It can't be exposed to a balcony overhang that's not insulated. So either way you cut it, it needs to be insulated on all 6 sides and have an air barrier on all 6 sides. So properly, hopefully I answered that. If not, just reiterate the question a little bit different. We'll go into it in more detail. So properly installed insulation consists of insulation. We talked about this. All 6 sides, top, bottom, with rigid backing and sheathing. Ensure that framing is correctly installed prior to the start of the installation. That kind of goes without saying. If you go and look at this, if you walk into like what we saw in the scary picture in the beginning, if you can actually see that and know that framing is not complete, you probably should not be doing an insulation inspection. Or, you know, you're telling them at a polysil stage what needs to be done. Yeah, you're right, Cody. The most common confusing lately is double walls. Thankfully, we talked about it last week that it's being addressed in the 2024 code. But double walls, common walls, demising walls, in townhouses being split, having that fire break that's there, you've got the gap between that. It's not fully insulated. It's not fully sealed. Or, as I talked about with a walkthrough, having a double wall at the back of a media room because you're hiding 2 flue pipes and you're hiding all your media drops, and then you're just netting all of that and not even capping it at the top. We saw that on prior webinars with that. You've got to actually determine where the thermal envelope is, and that all 6 sides of that insulation is in contact with what is considered the air barrier. Period. If it's not in any one of those 6 sides, it's a misalignment of the air barrier and thermal boundary. Period. Needs to be more in contact. Here is something ResNet finally updated. Thankfully, this has probably been years ago, and I just now did a search for it. But they finally updated their picture and their graphical pictures of what it looks like when you define grade 1, grade 2, and grade 3. So it's easier to look at it and to be able to have your eyes adjust to what that actually looks like. So grade 1 ensures insulation system is installed accordingly with manufacturer's installation instructions. The material completely fills the wall cavity. Air permeable insulation materials are encapsulated with airtight materials on all 6 sides. The material is also carefully cut around electrical junction boxes, split around wires and pipes, generally not compressed greater than 1/2 inch of thickness over less than 2% of the surface area. It looks something like this. So on the lower left of that, they're actually showing you that they have sheathing behind it. It's not missing insulation. They've cut it away so you could see the sheathing. And on the top right, you see the sheetrock is there. You see very minor compressions at the top. It's saying 1/2 inch or less gray area. It's compressed, not missing. It's compressed. Maybe there's a nail poking through. Maybe there's a sheathing nail that was punched through. It's leaving that there. I mean, maybe it's compressing some of that. And you've got the sheeting. Insulation in contact with sheathing on all studs. This doesn't say, and I'll have to reiterate this multiple times in the webinar, this doesn't say, but not here and not there. It just says all air permeable insulation materials must be encapsulated with an airtight material on all 6 sides. It doesn't say, but not on a garage wall under the stairs or not behind a fireplace. It's all of it to be considered grade 1. Anything outside of that is a grade 2 or a grade 3, period. Any of it. And then you look at the next one, grade 2. Grade 2 has some allowances for imperfections of installation, but overall, the minimal imperfections of the installed material, minor gaps, compressions may exist between 2 and 10% of the total surface area, typically 1/2 inch or less. Another important note is that grade 2 requires all air and permeable insulation to be encapsulated with airtight materials on all 6 sides. Still, grade 2 is telling you it needs to be encapsulated on all 6 sides. The insulation may have slight imperfections around electrical boxes or slightly rolled edges of the insulation. In other words, they friction fit it and it's slightly rolled at the edges. With this, that's kind of what they're showing here, but they're showing rounded corners at the bottom. They're showing slight compressions. It's against the wall at the sheathing and against the wall as the sheetrock. The hard part is you're asking for air barriers to be installed where there won't be sheetrock, like under stairs, behind fireplaces, under tubs. And if it's installed and it's insulated, you can't really see the insulation anymore. You can cut a hole and say, yes, it's insulated, but is it compressed? Is there gaps? Is there voids? You kind of have to grade that as, well, it is 6-sided encapsulated. The worst it can be is grade 2. And so the majority of what I've ever seen being installed is almost always grade 2. Grade 1, it takes some time and some expertise and knowledgeable installers to get there. Grade 3 is least desirable outcome for installation. It should typically require an installing contractor to return and replace or repair. This installation grade indicates more than 10% of the total surface is compressed, greater than 1/2 inch. And the encapsulation has not been achieved on all 6 sides of the air permeable insulation material. So you're missing stuff. So we always called out and red tagged for, hey, you don't have an air barrier underneath the tub. Well, yes, that's code required. But if I just said, okay, fine, if you want to leave it that way, I'll just do it as grade 3. Well, someone now needs to go inside the energy model and list it as a grade 3 or list the home as overall less than grade 1 and see if it determines whether it passes or fails the model. If it doesn't, it really should be red tagged and not allowed to go forward until it's corrected. but a lot of times we don't have in real time energy modeling updates or recalculating to make sure that it's passing. So Cody, yeah, some confusion, all 6 sides, vertical application and horizontal, because GCLA has to touch subfloor, but not drywall in the garage. Yep. I mean, that's a good way of doing. Yes, you're right. That does add some confusion a little bit. That's why we're looking for that R value. Is it correct? And is it in contact with the conditioned floor? Thankfully, again, Cody, that's addressed in the 2024 table, or the table there about each components. And it says it's excluded from having to be in contact with the unconditioned side. So yeah, it's a great point, Cody. And I'm glad with the new way of they're doing the code is that they're actually getting that in the book to be able to have that. So I'm glad they're addressing that part of it. But that shows you grade 3. And if you look at it, I mean, that's really bad. And all the gray areas compressions. And if you see OSB board, then you see that's a gap. It's a gap or a void of insulation. But what you have to look at is if you have a compression, once it's sheetrocked in the front, there will be a void of insulation directly behind the sheetrock. And that's what a third party or energy verifier or even a building official should look at and determine, is that correctly installed per the manufacturer's recommendations or instructions? And to me, it says no gaps, no voids, no or little compressions. That tells me that if I see a compression that's leaving a void behind the sheetrock, that should be a no-no. That's not, you now have to diminish the grade to a grade 2 or a grade 3, and depending on how much it's actually done. So type of insulation that we see, it doesn't really matter what type of insulation is used. What matters most is the R value per inch and how well it was installed. The worse it's installed, the worse the R value gets. But also, to quote the book, it says permanently installed, not temporarily, not just, well, it's going to hold in place. It's got to be permanently installed. So bat and blanket, wall and attic, loose fill, net and blow, cellulose, wet and dry, spray foam. Mostly what we see in residential is open cell. Then you've got continuous rigid foam board. So to start with that, it starts with the air barrier on the outside. So with this, an air barrier system is materials that restricts and prevents the passage of air through a building thermal envelope. Building's thermal envelope is the boundary between conditioned and unconditioned space. The air barrier is designed and constructed to control airflow and reduce energy loss. Air barriers also typically defined as the location of the pressure boundary of the building enclosure. So when you do a blower door in a house, technically what you're testing is the pressure boundary, which is also known as its air barrier. So if that isn't done right, you're probably going to fail some of that. So, and then Cody says, are you going to cover some of the new sprayed applied application protocols? I go through a little bit of the sprayed on stuff and what we're looking at. I don't know what protocols you're talking about, but if you want to send that to me, I can definitely do a complete webinar on that. It's important to note, though, in multifamily townhomes and apartment construction, the air barrier also separates the conditioned air from any adjacent units. So it's also the fire barrier, the smoke barrier in multifamily townhomes and apartments. The reason I bring that up is, if you were with us last week, it is addressed in the 24, and it's stating on there that each unit of these multifamily and townhomes and apartments need to have its own air barrier. It needs to be able to have its own contained air conditioning in it without bleeding into the units adjacent. So lastly, with a single family, the air barrier system also includes the separation from garage and the conditioned space. A lot of framers and insulators look at that as it's just an interior. It's not really an interior wall. It is, because it meets the interior side, but it's not an exterior wall. So they don't treat it as such, but it must be treated as such. And then can also be defined as a gas barrier, provides a gas tight separation between, or contamination barrier between garage and the rest of the house. So that garage wall, Energy Star talks about that specifically and has specific requirements for the garage wall, that it must be air sealed and separated completely from the rest of the home, not just treated as a separation of garage and home, and it just needs to be insulated. No, it needs to be airtight, air sealed completely for contamination. So with the air barrier, it's not just including the exterior wall. We talked about the garage wall, but also when you're determining and looking at and doing the inspections, you also need to determine what's the separation from conditioned and unconditioned. It's not just the outside. It can also be attic wall, knee walls, floor over ambient, floor over garage, floor over crawl space, and floor over all other conditioned spaces. So the energy verifier must identify all these locations to determine is the air sealing of the material being used in compliance and meeting the intent of the code. That's all seams are sealed, all gaps are sealed, all penetrations are sealed, all the material is installed per the manufacturer's instructions. We talked about these before and prior, but what you'd see kind of out there is T-ply, house wrap, zip board, polyiso being used as an insulator and an air barrier, and then of course OSB as well. So thankfully, all of these can be used and considered as an air barrier. We talked about it multiple times before, but it's important enough to state again is must have the correct nailing pattern, must follow manufacturer's instructions on butted or overlap seams, and then all penetrations must be sealed. This really goes with saying T-ply, T-ply, T-ply. If it's not installed correctly and stapled per manufacturer's instructions, it will be a very poorly installed air barrier. And also with this, we saw the home like on the right. We saw a lot of that throughout the supply chain issues and supply shortages. We've got zip on the left, which is really good. It's actually consistent and it actually butts together. You have a proper tape that needs to be done. You have to follow a certain protocol to tape those seams. But when you have multiple different styles of materials, we got T-ply, we got whiteboard, we got the gray board, we got OSB. Sometimes we'll have an R3 board. They all have different thicknesses. And so, but whatever means are necessary needs to be taken to air seal these correctly. So we see the OSB is being overlapped by T-ply. Is the T-ply stapled correctly to the OSB to where it makes an airtight seal at that point? If not, needs to have some kind of tape there, some kind of air sealant there. And then when the seams butt together, they're taping that as well, but they also still need to make sure that they nail that per the nailing pattern required by the manufacturer. The air barrier also includes, so when you have the attic area and then you're looking at a home, anything in the attic, now you're going to have sheetrock or drywall separating that. That becomes your interior air barrier on the separation from attic unconditioned spaces and the home. So with that, all those need to be sealed. As we see on the right-hand side, this is, some people say it's extreme. In my opinion, it's what should be done on all houses. You see a gasket, either a caulking gasket, a poly gasket, or a foam gasket being rolled out and stapled on all of these areas around window openings, around door openings, around the base plates, around the top plates, all of it, and even at the T-wall intersections. Needs to have all of this done. It needs to have all those sealed. Thanks, Cody. I'll look that up in just a second. It needs to have all those places sealed, and any penetration through the sheetrock must be sealed. So now we'll move on to what these things look like. So knee walls. Sometimes knee walls are not obvious. They can be hiding in plain sight. So like the one on the left, it's very small. It's a little triangle, but that's still what should be considered a knee wall. It needs to have an air barrier on the back side facing the unconditioned space and air sealed on all sides. The one on the right is a good example of the air barrier and properly air sealed. Both those holes at the top plates, they should also be poly sealed. Hopefully maybe it's poly sealed on the top inside that cavity. It doesn't look like it. So it should be poly sealed as well. The one on the left, so here we see the same kind of knee wall, but the one on the left is air sealed and insulated. The one on the right isn't. It doesn't have to be because the one on the right is in the encapsulated attic. It's in the building's thermal envelope. Doesn't have to be air sealed, doesn't have to be insulated. However, this picture is showing a misalignment of the building thermal envelope. So I should not be able to see daylight coming from the other side of that knee wall. That's showing me that there's a gap in the insulation and the thermal envelope is not complete. So we'll see what that looks like more in a few slides later, but that's a misalignment of the air barrier. And it happens a lot with foam, a lot. This looks correct to most people doing the framing and doing the insulation. It looks correct, but if I went over that knee wall and jumped to the other side, that's either a garage or that's either the outside, and that is not correct. It needs to be a complete alignment of the air barrier and the insulation for the thermal boundary. In my opinion, this is a misalignment. We'll see what that looks like later and to why it's a misalignment. So attic knee walls and just a knee wall or attic knee wall, all of them must have an air barrier facing the unconditioned space. The spaces between each of those ceiling joists, if you look at that, there's a floating gasket. So that's telling me that something's missing. It's blocking that's needed to stop the attic air from moving into the cavities. This is probably not an insulated wall. I mean, the insulation probably has not been installed yet. Otherwise, we'd see insulation laying up against that on partial part of that lower wall on the ceiling area between those ceiling joists. But that floating gasket, those guys knew that that was the boundary. They knew that was the boundary of the thermal envelope. So they put a gasket up, but no one framed it correctly. So there's no stopping air going from those points all the way up into the cavity that's inside, facing adjacent to a conditioned space. Blocking needs to be added directly behind the gaskets, and then all gaps in that blocking needs to be sealed. Wall cavity installations, we saw these photos in previous webinar that we did. These came courtesy of Michael with the city of North Richland Hills. So the two on the bottom actually was what it looked like before, and then he called it out and said, I need this corrected because it's not meeting what needs to be done for the installation instructions of manufacturers, especially with craft face paper. It's so much easier to get a grade 1 by just stapling to the face. They were just trying to friction fit it like they did all the other bats that they used, and it wasn't done correctly. So the top of this actually shows it being corrected. So looking at both of these photos, we see that small differences in installation quality, enough to lower the grade from a grade 1 to a grade 2. So looking at that, where the verifier now needs to look at it and determine the percentage of gaps, voids, compressions, and accurately record the grade of insulation. So looking at what we saw with the graphical pictures, or the pictures that ResNet sent out, would you determine that the one on the left is grade 1 or grade 2? I personally would like that. I would grade it grade 2 on the left, and I would grade it grade 1 on the right. We talked about it before, though. In the energy model, you can't do it really by component. I mean, you can do it by component, meaning as the floors, grade 1 or grade 2. But if you have a section of wall that is not meeting grade 1, you can't just say, well, 100 feet of grade of the south facing wall is grade 2 where the rest are grade 1. You have to do an overall. Well, if it's not quite enough square footage that's poorly installed, is it going to be detrimental to the entire overall grading of the house? So that's what you have to determine. The one on the right looks really nice. It's easier to get done better if it's a high density bat because it doesn't compress as easily. So when they friction fit this in, it kind of rebounds after you do that because it has a denser material. The one on the left is not high density bat, so when you compress it, it almost stays at that point. So net and blow is easier to obtain a grade 1 install, but in these two photos, can you spot the difference? So the one on the left is more densely packed than the one on the right. In my Raider opinion, it would be that the one on the left is R15. They're upholding the density required for R15 in wall blow. The one on the right, I would almost list that as an R13 and have to compare the certificate and the energy model to see which way are they actually doing that. Is it 13? If it's 13, that's probably fine. If it's 15 and they're trying to get credit for that in the energy model, I would have to question whether or not that's densely enough. Because you see a lot of the dark patches in between, a lot of the gray areas, that's a dead giveaway that it's not fully compacted and densely packed like it is on the left. So if you use an open hand and press against the cavity, you should feel resistance on the one on the left. It can sort of rebound. If you don't feel resistance and it leaves an open pocket as big as your hand behind all of that netting, that probably should be listed as 13, or even question whether or not it's actually has the right density installed to meet an R13. Because what's going to happen over time is that insulation is going to compact. It's going to leave a gap at the top. It might look good now, but eventually it will start to collapse on itself just due to the weight, and it will actually make that difference. So in my opinion, the left is a grade 1 R15. On the right, if it's 13, I'd probably list it as a grade 1 because it's fully filled and it will be in contact with all 6 sides. However, if it's really, really not that dense, you might question the fact that is that really meeting an R13? Another easy determination is grading of foam. So if installed per manufacturer instructions to achieve the proper R value, it's almost impossible to get a grade 1. What usually happens is the installer will install less than the inches needed for the R value required. So the photo on the right is one way to verify the depth and thickness to ensure proper R value. This is just a meat skewer that I bought off of Amazon, and we put tape on the 3.5 inch mark and tape on the 5.5 inch mark. We actually poke that into the cavities to verify compliance with the depth that's required. So if I'm able to do that, and overall the average is about 3.5 to maybe a 3, then you're looking at roughly an R13 wall, and that's what it should be listed as. And so here, looking at that, I've deemed that as a grade 1 install. It's touching the bottom of that orange tape. That's a 3.5 inch depth. They're meeting the R value per inch as an R13 wall. On the left-hand side, they've got a few pockets of that, but overall, that's done very well. They've achieved what they needed to in a grade 1. Here's another shot of a really good foam install, but if you notice how different the vaults look compared to the wall, if the cavity depth of the vaults is 5.5 inches because it's framed with a 2x6, and the required R value is R19, then what depth of the open cell should I be seeing? So if I do it with a probe and look at that, will it hit the black tape as 5.5, or will it hit something different? So looking at that, Google lists open cell foam as having an R value per inch of 3.5 to 3.6. So if that's true and we do the math, then if it's a 2x6 wall, it's 5.5 inch deep. So that's 3.6, giving them the advantage of a higher R value. That equals 19.8. So, and if the requirement in that climate zone is R19 in vaults, then shouldn't I be seeing most of that cavity fully filled? So to me, that's a lot of void, that's a lot of gap. But if for some reason this is 2x8s, then this installation would be okay. Because once you spray foam beyond 2 inches, it becomes its own air barrier. It is in contact with an air barrier on all 6 sides. It's not like the open bat with trapping of the air pathways. It doesn't have to be in contact with the sheetrock in front of it. It makes its own air barrier. So those voids are okay. But again, listing it as grade 2 is another way of saying it has less R value, because anything less than grade 1 diminishes the listed or labeled R value. So if I said that's 19, but it's grade 2, it's really going to list it less than that. That's going to change the model, and it may or may not fail the model. And that's how it continually starts to work with failing the model, or making sure that it passes. We can't forget these, though. If insulation is not visible for inspection, really what the verifier should do is grade everything that's not visible as a grade 3. If you can't see insulation, or hopefully you can see insulation around the openings, so you know it is insulated, but it should be graded as a grade 3. The biggest problem with floors over anything, even if they're insulated, is the insulation in proper contact and permanent contact with the correct surface. So is it permanently held in place? These cornice boards should actually be removed. Insulation must make sure that it's verified to be touching the right condition surface, as well as being held permanently in place, not just friction fitted, should be permanently held in place. So most builders, the cornice guys get ahead. They go around and just start putting up cornice boards because they're trying to stay on track with scheduling. And then the insulators haven't come out. It's either not insulated or it was pre-insulated, but you don't know if it was done correctly. And then the cornice board goes up. Has to be removed to actually verify compliance. In both of these pictures, it's incorrect. So large gaps on the left, not fully filling encapsulated on the right. Even though the one on the right looks to be in conditioned space or facing a conditioned space, it's actually in a dead space that's not capped at the top. I did this inspection. I took this photo. The top of this chase was not capped, so we were asking them to cap that, as well as now you have to put air barrier behind all the interior walls and the chase walls. But what they were going to do is they were going to cap the top of that chase, and that's fine. However, now that the air barrier is at the top, but the insulation is at the bottom, it's a misalignment of the thermal envelope. You have now split the air barrier and insulation, which per manufacturer's instruction says it must be in contact with the air barrier on all 6 sides. If not, it's a misalignment. It's not properly installed. With this, we see both of them correctly installed and held permanently in place and in contact with the conditioned space. This is an R22 bat in 1. That's looks like TJI's Now looking at that closer, it may or may not actually be in contact with the conditioned side. That probably should be held in place with some wire stays because 22 is only about 5.5 to 6 inches deep. I know those TJIs are about 10. That probably isn't correct, or it's double lined with two pieces of insulation. The one on the left, holding it in place with a styrofoam board. They're stapling those in place and permanently affixing that bat against the conditioned space. That's done correctly. But when you look at the next ones, floor over garage tends to be where the installers get kind of laxed. So all three of these photos show it to be insulated, but most of the one on the left is being overly compressed, causing each of the sides to collapse, leaving voids directly underneath the conditioned floor above. And then the two on the right, none of the insulation's in contact with the conditioned floor above. They're held in place with wire stays, but they're not in the right location. It looks nice, it looks pretty, but the one right there on the below and the bottom, I took that photo, I pushed the bat out of the way, and there's a massive gap to where it goes to the conditioned floor. I could tell it wasn't double lined. It's only 6 inches deep. Those TJIs are 10. That's a massive gap that's there. They're going to have to fix that. And the one at the top, I also took that one as well. Took a stick in the ground and just poked up one of those bats, the one closest to us on the left. I just pushed it. And when I pushed it, it went all the way up and left a massive gap, which told me that that's not properly installed. So it should be corrected. Here we just see three that were correctly installed. So the top left is traditional TJIs, the top right is open cell foam, and then the bottom is through the truss system. So those are all being done correctly. With the foam, as we said earlier, once it's beyond 2 inches, it makes its own air barrier, so it doesn't necessarily need blocking on all the edges. All other flooring type material, bats, or anything that's netted and blown, all has to have air barriers on all 6 sides. And as Cody said earlier, it may not be in contact with the garage ceiling, but now code's getting to the point where it's addressing that and saying it doesn't have to be. As long as the R value is there and not fully compressed or compressed at very little, it's going to comply with that. And then don't forget these. I've put this in several of my webinars. The floor over garages. It's not necessarily a floor. It's an extension of the second floor that kind of overhangs a little bit of the garage. Even though this looks decently insulated, still needs blocking between all those floor joists, or in this case, the ceiling joists of the garage. It needs all those to be sealed at the end. It needs to have blocking there. It needs to have ceiling there. It needs to be capped and enclosed on all sides. It can't just be left. If it's R38 and it's exposed to the attic, it doesn't necessarily need to be enclosed at the top if it's that way. But if there's a floor above it at all, it needs to be in contact with the floor, and then in contact with the band joist, in contact with the sheetrock on the top of the ceiling of the garage, and then have blocking on the back side of it as well to keep that enclosed. And of course, you've got it sandwiched in between the two ceiling joists. This is what I talked about earlier about misalignment of it when you're looking at foam, what we saw looking over the knee wall and saying this isn't correct. This is me standing in the garage. I'm in the attic above the garage in a foamed encapsulated house. So they've moved the demising wall or curtain wall of that further out over the garage. However, there's a huge portion of the floor over the garage that isn't being insulated. And if that's what's now considered a conditioned space, it's a misalignment of the thermal envelope. There is a way to look at this. It has to be. There's different ways they can do this. It can be, you can move the demising wall and add another one and move it closer to the top of the garage wall, or they're going to have to go back and they're going to have to foam the ceiling over the garage to complete this thermal envelope. So that needs to happen. It's a misalignment of the thermal boundary and the thermal envelope. So it's tough to call out. I hated to call this out. The framers did it correctly. They put the demising wall where it needed to be. The insulators did their job, but no one made sure that the floor over the garage was being insulated, which now needs to be insulated because now you're leaving an uninsulated ceiling or floor of the encapsulated attic, which is part of the conditioned space, exposed to no insulation. Needs to be done. Rim joist with this, we're looking at just the way it looks differently. We talked about it last week in the 2024. It now is called out that these must be held permanently in place, not just friction fit. The one on the left is R15 bath. It's friction fit. In my opinion, is not permanently held in place. Foam, of course, is not going to magically fall down, we hope. As long as it doesn't delaminate, it's going to stay there forever. So that's permanently held in place just by the way it's done. And then we've got attic insulation. It's pretty easy. Usually, if you make sure that the markers are done correctly, it's easy to see that. If it's all level, it's not peaking at all the markers, it's grade 1. If it's meeting that R value. On the right, we've got foam. It's an encapsulated attic. You see the peaks of every single rafter. They covered each rafter, which in my opinion is a great way to do it. You're blocking thermal bridging to happening at those peaks of all those rafters. So you're making sure that's all covered. And you're also looking at the fact that it's, if you see those rafters being covered like that, you can assume that if that's a 2x6 rafter, that it's actually 5.5 inches deep. Brad asked, does mid-floor insulation count to hold in rim joists, or does it need to be mechanically or encapsulated? Does mid-floor insulation count to hold in? That's a good question, Brad. And does it meet the intent of being permanently held in place? And that means making sure that insulation stays in contact with the rim board. If it doesn't, and it's going to fall, then that's not permanently held in place. So it needs to be mechanically held in place, or, as you said, encapsulated with foam. So you're right, and that's correct. So just having something there and saying, well, it's inside of a conditioned floor, doesn't mean it's held permanently in contact with its air barrier, which is the rim board. So good question. So looking at that and part of it, I mean, a lot of times it's easier said than done to get up there and actually pinprick, or using a skewer or a depth marker and actually trying to see what the depth is on this foam. But seeing rafter tops, knowing that that's 2x6 framing, you can actually determine that's 5.5 inch and the rafter tops are being covered. That looks uniform to me. So 5.5, and that equals R19 or R20, 21. But it's a whole different conversation as to, does that meet the attic or ceiling requirement R value of the energy code? Whole different conversation. Attic insulation as well. We talked about this, looking at that, determining it, having the liability of having a certification from the installer being directly or immediately installed after installation of the material is required by code. So if you're doing foam, I need to see a certificate at pre-drywall posted immediately after install that shows me what I'm supposed to be looking at. It determines what the R value per inch is, what material was used, what depth I should be seeing in each cavity. And then, of course, traditionally, you'll see a certificate in the attic showing the attic insulation being blown, number of bags, what's the coverage on each of those bags per square foot. All that being done needs to be posted. That's moving the liability to the installer, saying that he did his job correctly. And so when you're doing your inspection, you're looking at it and saying, yes, it's correct, or I have questions of whether it's correct, the liability falls on the installer. Can't go without saying, though, is Energy Star has its own separate requirements for that. We're now into version 3.1. This is revision 11. I highlighted the one that says all insulation achieves grade 1 install, period. We already read what that means by ResNet standards, grade 1, grade 2, grade 3. Energy Star says you're going to meet that. It also says in here that advanced framing must be used. It also says at exterior vertical surfaces of wall insulation in all climate zones, also in interior vertical surfaces of wall insulation in climate zones 4 through 8, you must have an air barrier behind tubs and showers and fireplaces. This is where all this was coming from with the DOE and the Department of Energy putting it in their Energy Star requirement. Now code requires the same thing. It always has, but it just says follow manufacturer's instructions, which lists it must have air barriers here. But Energy Star goes to the point of saying it has to be here. And then it talks about floors. It talks about thermal bridging, using advanced framing, all of that being done. Minimum stud spacing of 16 inch on center for 2x4, and then framing correctly around windows, having insulated headers, not over framing around windows, having one pair of jacks, one pair of kings, not overdoing it and have more and more pieces of wood there for thermal bridging to happen. So note 5, when it says on here though, when it says all insulation achieves grade 1, there is a note there. It says note 5. It says only 2 alternatives are allowed. Grade 2 cavity insulation is permitted only if they're using continuous insulation on the outside with an R value of at least R3 in climate zones 1 through 4 and R5 in climate zones 5 through 8. The reason I put this in here is because we're seeing more Energy Star being used as a pathway. When you're out there and the city officials are looking at it and you know that it's being Energy Star because you've seen the permit documentation, just know that they need to meet grade 1 on all insulation components except on the exterior wall and attic walls. If they're using R3 in this climate zone, if they're using R3 board on the outside, it can be grade 2 and still pass. Grade 2 bats are permitted to be used in floors if they fully fill the cavity touching all 6 sides. So as long as they're doing that, then those 2 things are permitted. That's why they put the footnote in there for those different areas it can be done. Now that the different parts and the different section of what this webinar was all about was how much difference does it really make? What I did was ask a third party to run some energy modeling, use the same house, use the same criteria. So we got examples 1, 2, and 3, which is a grade 1, a grade 2, and a grade 3. All these reports come from Ecotrope, which is one of those softwares that are being used. They're all based on the 2018 IECC compliance using the North Central Texas COG amendments, which actually allows up to 4 ACH instead of 3 ACH for the 2018 base code. All 3 of these are the same house. They're 2 stories. They're 2,300 square feet. They're 4 bedrooms. They're based in the Dallas area. There's no floor over ambient. All things are equal. The R values are equal. The U factors are equal. The SHGC is equal. The mechanicals are equal. The only difference is that the grade of the installation on the exterior wall and the attics and here are listed as grade 1, a grade 2, a grade 3. All of them do have grade 1 attic installation. The only thing I ask them to do is wall insulation. So how much difference is it going to make when you have a poorly installed exterior wall? So here we see if it's looking at the annual energy cost of the design and it's comparing it to the proposed, well, proposed is the design, but you're looking at referenced, and the reference is the North Central Texas COG amended 2018 IECC. It shows a total consumption of energy for the annual use, $1,891. As proposed or as designed, it's equal to $1,891. So here it says design exceeds requirements of the actually it meets, and this one actually shows exceeds. Sorry, it didn't change the dollar amount, but it's 0.3%. So that's grade 1. And as you see on the below that, all the check marks are green, saying that they've met all of these requirements for that. Now, the only thing difference that I've done is change it to grade 2. So the annual energy consumption rose by $13 a year. Doesn't sound like a lot at all, and it's not a lot at all, but it now fails the model at 0.7% over energy consumption. So if before we're meeting exactly, now we went 0.7, not even a percent over, and this fails the energy model. Permit documentation should not be stamped as approved until this is equal to or better than the energy consumption in the report for the referenced home. So you should see 1891 or better just to be able to pass. If you see big red letters, of course, everyone knows that's not good. And it says on here, based on these elements, for it's not in code field enforcement, and it does not pass the energy model. So this should be red tagged. It should be reconfirmed from the energy modeler. If I do grade 2 here, do I still, and can I still pass energy code? If they come back and say, no, it now fails the model, red tag needs to be corrected. If they say grade 2 does pass, then you can record it as grade 2 and move on and say that you're still in compliance with the permit documentation to meet the levels of acceptance for whatever pathway and whatever code version that's being used. And then we went to grade 3. So the annual consumption now rose another $19 from grade 2 to grade 3. That's a total of only $32 a year, which isn't much at all. And to me, no one's going to laugh. I mean, they're going to look at that and just kind of laugh and go, well, that's only $32 a year. I mean, I can sneeze at that and spend it extra money at lunch to do that, and it still costs the same thing. And I agree, but you can't fake the numbers at the bottom when it says it now fails by compliance by 2.2%. So it's not just the dollar amount that changes. What also changes is CO2 gas emissions, natural gas consumption, and of course the total electrical consumptions of the whole building. Lastly, if the builder is also following an ERI path, the score did change from 1, 2, and 3 by 1 point. Not a lot, but it did change by 1 point. So if you're following the ERI path and you're saying I need to hit 56 and it moved to 57, then you failed. You failed energy modeling, and the models actually failed. Permit documentation should not be approved. It should go back and be readjusted for to be done. The problem is it's normally when you do a design proposal, they're not going to turn one in that says fail. They're going to turn one in that says it complies. Now it's up to the inspector or the third party or the building official to look at it and identify anything less than required. But as we saw earlier on the grade 1, that means everything is done precisely to manufacturer's instructions, hitting grade 1 on every single component of the building in order to just barely meet base code. Anything that deviated beyond that has now failed the energy model. That's how shoestring tight some of these are. They don't design the home to meet energy code by 20% because that's going to cost too much in construction. They're going to say, tell me what I need to meet right at code level so that I can hold my costs down. So when you go in and look at a house and it's insulated but poorly insulated, technically that's not going to even pass code. That's not passing base code. That's not passing the energy model. And if it isn't reconfirmed through the energy modeler and determined that grade 2 or grade 3 is acceptable, then technically it should be red tagged on site and forced to be compliant with the code. I know it's a gray area. I was, again, given the captain red tag title. I understand that red tagging the builder isn't as easy as it sounds, and it's not a cakewalk. People get upset. It slows construction. It costs them more money. I understand that. But once they understand that this is not going to be acceptable, that's where the enforcement comes in. Then the installers are just going to learn how to do it better, in my opinion. But you get new crews all the time. And when those new crews come in, they have to be retrained. And if they're not retrained properly and they're installing it by the piece and they're going as fast as they can, you're going to get poorly installed insulation. And when that happens, the energy model should be updated. And if it's not, then it's a disservice to the actual building itself. And it is increasing the energy consumption for the building, for the life of the building. So we're looking at $32 a year. And if I take $32 and multiply it times, let's just say 50 years, $1,600 over what we would consider the life of the building of a house being built to code. Is that detrimental to someone's pocketbook? Maybe not, but we all know that energy, the cost of energy is not going to go down. It's only going to go up. So that 16 can turn into 2,000 and then it can turn into 2,500, but that's over 50 years. I get it. It's not a lot of money, but it also means that it should not be allowed just to be let go and passed as grade 2 or grade 3 when it technically by code standard needs to follow manufacturer's recommendations or instructions, which we just saw completely spells out grade 1 all day long. So that pretty much is the end of this. Join us for our next webinar coming up next week. It's the part 2 of the 2024 IECC residential, what we know so far. I'm basically just going through what I see as the closest. It's not final, but it's the draft that shows what's actually made it into the code. It's Thursday, November 2nd. It's at 10:30. It's an hour and a half long. So join us on that, and we'll finish that up. That is for residential. I will be going through commercial. And yes, Brad, if you're still on the call, I will try to include a lot more multifamily stuff as well, so we can look at what that looks like for multifamily, not just looking at industrial buildings. It's looking at what's considered commercial when it's 4 stories or higher and it's apartment buildings. So I'll try to include more of that in there. So thanks again for joining me. Here's my contact information. By all means, screenshot this, shoot a picture with your phone, share it with who you need to share it with. I'll help in any way that I can. We'll go through the code book. Ultimately, I had a call this morning and it ended up being, I'm sorry, I was reading Christian things. Yes, you're right. But ultimately, it comes down to a code official approval. If there's a conflict and somebody has to make a call as to right or wrong, it comes down to the code official has final say. So if there's an argument between the builder and a third party, then you need to go talk to the code official in charge of enforcement and say, what would you like to see here before moving forward? The call I got this morning was from an architecture firm that actually was asking that question because a third party entity was asking for something beyond the city adopted ordinance. And I just basically told him he's going to have to go back to the city and ask for the what do they want to see happen. So thanks again, guys. I appreciate your time and thank you for sticking around to the end. I will now end the recording. I'll hang on here. If anybody's got any additional questions, I can unmute you if it's harder to ask the question than to type it out. So again, thanks for joining us, and I will see you on the next one.